welcome you all to session 2 of the chapter Angular Momentum. In this session, we will be discussing about torque. So what is torque? Torque is the rotating effect of force. Torque is analogous to force in case of linear motion, right? When a body is moving in a straight line, we speak about force. When a body is rotating, we speak about the torque. So torque plays the similar role as that of force. Okay, let us check it out what actually the torque is. Let me consider a body of mass m which is rotating in a circle like this. Okay, let me consider this is a particle whose mass is m, right? So this is the center, right? This is axis of rotation and the body is revolving like this, right? Okay, and the force which acts on this particle, let me take like this, right? If I apply the force, then only the body rotates, right? Okay, what is the force acted on this particle? In this direction. So the position vector of this particle is, let me take it as r, right? Okay, now the torque acting on it is given by, do remember, torque is denoted by tau, right? So if you want to calculate torque now here, torque is the vector product of position vector into what we say here, force. So torque is vector product of position vector and force, right? It depends upon the force acted on a particle and also it depends upon distance from the fixed points. So let me call this torque as moment of force. I already used the word called moment. Moment is a word which can be used when you take a physical quantity with the distance. Here what is the physical quantity? F, and this is the distance, right? If you take a physical quantity with the distance, you can use the word called moment. So what is torque? Torque is moment of force, right? Okay, let me write the definition of torque. Torque on a particle, torque on a particle is defined as, how it is defined? It is defined as moment of force. Moment of force. Do you remember? It is defined as moment of force. What is the moment of force? Position vector into force, right? Moment is a word which is used when you take a physical quantity with the distance, right? I am taking a physical quantity with the distance from a fixed point. That time I can use the word called moment, right? Okay, torque on a particle is defined as moment of a force, right, about the fixed point, right? About the fixed point. Which is the fixed point now here? Let me call O as the fixed point now here, right? Okay. Now, torque on a particle is defined as moment of force about the fixed point. Imagine this is a disk now here, right? This is the axis of rotation and I am just applying a force to it and it begins to rotate. Where did I apply force? At this position I applied force, right? So, let me multiply the position vector and force, we get the torque, right? Okay, means the rotating effect not only depends upon the force, it depends upon the distance of the particle from the axis of rotation. That's why we need to take both force as well as distance, then we can speak about torque. So what is torque? It is a movement of force, right? Okay, torque on a particle is defined as moment of force about the fixed point. And how to measure that? I have already written. It is measured by, okay, it is measured by vector product of, it is measured by vector product of, it is measured by vector product of position vector and what we say here, force, right? It is measured by vector product of position vector and force, right? So the formula for a torque, that is tau, is equal to R cross F. Do remember this, right? Okay, as it is a vector product, this torque is which quantity? It is a vector quantity. Do remember, torque is a vector quantity. Whenever I speak about vector quantity, I need to tell about its direction, right? So you know that whenever you take the vector products, the direction of the result will be perpendicular to the plane containing these two vectors, right? Okay, now let us check it out. What is the direction of torque now here, right? Okay, now let me speak about direction of torque. Direction of torque. Direction of torque. Direction is perpendicular to the plane containing perpendicular to the plane containing, which are the plane containing R and F, plane containing R and F now here, right? Okay, where is R? R is on the plane. Where is F? F is on the plane. Then where is torque? Torque is perpendicular to the plane. Either it is towards the observer or it is away from the observer, right? How to calculate it? We know that we can use a right hand thumb rule here, right? Okay, so curl the right hand in a such a way that from position vector to force, if I am curling it from position vector to force, the direction of thumb gives direction of the torque. Means if the particle is rotating in an anti-clockwise direction, the direction of tau is perpendicular and it is towards the observer, right? So if it is rotating clockwise, it will be away from the observer, right? Okay, do you understand this? Direction is perpendicular to the plane containing R and F, and this at this point the direction is towards the observer. It is perpendicular to the plane, right? Okay, now after studying what is the direction here, right? Okay, let me write this equation in a broader sense now here. Let me write like this: tau equal to R cross F, right? Okay, we know that. What is the formula for A dot B? A cross B, that is modulus of A modulus of B with theta sin theta, what we say here, n cap. N cap gives the direction of tau now here, right, which is perpendicular to the plane containing, what we say here, R and F, right? Okay, means when is torque maximum? Torque is maximum if angle theta is, what we say here, 90 degree. What is theta? Theta is angle between R and F, right? If angle between R and F is 90 degree, then torque is maximum. Okay, just check it out. What is the angle between R and F now here? The angle between R and F is 90 degree. If it is 90 degree, it rotates now here, right? Okay, if it is less than 90 degree, of course there will be force. Of course there will be torque now here, but it will be less now here, right? So it also depends upon angle between R and F, right? So torque will be maximum. Torque is maximum when R is perpendicular to, what we say here, F. That is why we take force perpendicular to R to get torque maximum, and torque is minimum, right? Torque is minimum when R is, what we say here, parallel to F. If R is parallel to F, torque is minimum here, right? So it is 0, right? If I am taking force in this direction, if I take that force in this direction, will the body rotate? No, because the torque at this time is 0, right? Okay, do remember, torque is maximum when R is perpendicular to F, torque is minimum when R is parallel to F here, right? So this was all about the torque. Do remember, torque formula is R cross F. Now let us take its SI unit. Okay, what is the SI unit now? What is the SI unit of torque? SI unit of torque. What is the SI unit of position vector? Position vector means distance. It is meter, right? What is the SI unit of force? It is Newton, right? So then what is the SI unit of the torque? That is meter into Newton, or we can write it as Newton meter, right? The SI unit of torque is Newton meter, right? Okay, now after studying SI unit, let me move on to dimensions. What are the dimensions of torque, right? Okay, let me write the dimensions here. What is the dimension of position vector? That is distance, that is length here, right? What is the dimension of force? You know, what is the formula for force? Mass into acceleration. Shall I write now here? That is mass m, acceleration L t raised to -2. If I combine that, I will be getting the dimensions of torque. Okay, what are the dimensions of torque? Shall I write like this? Okay, how many m do you have? Only one. Shall I write m raised to 1? How many L do you have? 2 L's. 1, 2. Let me take 2. What is t? T raised to what now here? -2, and this is the dimensions of torque. To know the SI unit and dimensions, you know the formula first now here, right? You must know the formula. So what is the formula for torque? That is R cross F. Based upon that, I have written SI unit as well as also what we say now here, dimensions, right? Okay, I already told you that torque plays a similar role as that of force, right? Okay, torque can also be defined like this. Okay, I think you know about Newton's second law, right? What does Newton's second law says? It says that the rate of change of momentum is directly proportional to the force, right, and takes place in the direction of force itself here, right. So we have the formula for force. So what do you have the formula for force? F is equal to dp upon dt, right. This is in case of linear motion, but when we take this in case of rotational motion, what happens now here, right? Here force, in place of force, shall I write tau, right? Torque plays a similar role as that of force. Now here we have which momentum? Linear momentum. Now I need to take angular momentum. Shall I take angular momentum? Yes. So instead of P, shall I take what now here? J divided by dt. Do remember, right? So this holds good, right? We can take Newton's second law to define torque in that way also, right? Okay, let me write now here. Torque can also be defined as, it is also be defined as the rate of change of angular momentum, or it can also be written like this, time rate of change of what we say here, angular momentum. Torque can also be defined as time rate of change of angular momentum. Shall I write like this? Torque, tau is equal to dj vector divided by dt, right? This is from Newton's second law, right? So remember, it is analogous to force now, right? So tau can also be defined like this. It is time rate of change of angular momentum, right? Okay. And another thing what you need to know here is, if a body is rotating, okay, just analyze, before I apply the force, the body is rotating. Okay, let me take the body is rotating. When you apply the torque, what happens to this? It gets acceleration, right? If it is moving slowly, if the body is rotating slowly, if I apply the torque, it rotates fast. Means what this body got now here? It got acceleration. Which acceleration? Let me call it as angular acceleration, because it is rotating, right? Okay, let me write about this. When torque acts on a rotating body, what happens? Rotating body about an axis of rotation, okay, what happens when torque acts on a rotating body about an axis? Means already the body is rotating, and if I apply the force, what happens? If it is already rotating, apply the force, its speed increases, right? What happens if speed increases? The body gets accelerated, right? Okay, now when torque acts on a rotating body about an axis, it produces, what does it produce? It produces angular acceleration. It produces angular acceleration, right? The body begins to rotate much more fast, means the body gets angular acceleration. Means there must be some relation between torque and angular acceleration, right? Okay, when torque acts on a rotating body about an axis, it produces angular acceleration. Now let us find what is the relationship between torque and angular acceleration. Okay, the next slide reading, let me take like this: relation between torque and angular acceleration. Let me take like this: angular acceleration, right? When a body is rotating, when you apply torque to it, its speed increases, means it produces angular acceleration. Now let us take what is the relationship between torque and what we say here, angular acceleration, right? So angular momentum of rigid body, shall I take like this? Angular momentum of rigid body. Angular momentum of rigid body. We have already derived in the last session what is the relationship between angular acceleration and angular velocity. So what was the formula? That is J is equal to I into angular velocity. Let me take it as omega, right? So angular momentum of the rigid body, we have derived it. That is angular acceleration is equal to product of moment of inertia into angular velocity. Now, shall I differentiate it? Because I want torque now, right? So I will be differentiating it. Shall I write like this? Differentiating with respect to, right? Differentiating with respect to time t. Shall I differentiate it? Okay, what do I get? Differentiate now here. dj divided by dt, that is equal to, shall I take like this? That is I dw divided by dt. Let me take moment of inertia, it is constant. The change is with respect to velocity, so I apply the differentiation to the velocity. Okay, what is it? dj by dt? We already seen that from Newton's second law. If you apply the Newton's second law for the rotating body, dj divided by dt can be written as what we say here? Tau, right? Okay, there is I now here, right? What is dw by dt? Differentiation of angular velocity. The differentiation of angular velocity is angular acceleration, right? Tau is equal to I into alpha, and this is the relationship between torque and what we say here? Angular acceleration. So what is the formula? That is tau equal to I into what we say here? Angular acceleration. Is it similar to the formula for force? Yes, we have. What is the formula for force? F is equal to mass into acceleration. Let me write the similar formula for rotational motion. What is the rotational analog of force? Rotational analog of force is tau. What is the rotational analog of mass? When we speak about mass in linear motion, in rotational motion, I speak about moment of inertia. In linear motion, I speak about linear acceleration. In rotational motion, I speak about rotational acceleration, that is angular acceleration, right? So, is this the same formula? Yes. What is this? This is a formula which is similar to F is equal to ma, right? Okay, do remember this. This is the relationship between torque and angular acceleration. Do remember, when a torque acts on a body, it produces angular acceleration. So, what is its formula? That is tau is equal to I into alpha, where alpha is, what is alpha now here? That is angular acceleration, where alpha is angular acceleration. Now shall I write like this? Torque is the product of what we say now here? Moment of inertia. Torque is also given like this now here, right? It can be written like this. Torque is the product of moment of inertia and what we say here? Angular acceleration. Do remember, right? It is the product of moment of inertia and angular acceleration. So this formula is similar to the formula F is equal to ma, tau equal to I into alpha. So this is the relationship between torque and angular acceleration. Now let us derive the relationship between angular momentum and torque, right? This is important one. Let us check it out, right? Okay, let me consider a body which is rotating about the axis. This is a body which is rotating about this axis of rotation. Let me consider a particle of mass m which is rotating with the velocity v. Let r be the position vector of the particle, right? If it is rotating with velocity v, it has linear momentum. So what is the formula for linear momentum? Mass into velocity. Okay, let me write about this. Consider a particle of mass m. Consider a particle of mass m rotating about a fixed point, with velocity, let me take with velocity v and rb position vector of the particle, right? Okay, let r be position vector of the particle. Now let us take what is the relationship between angular momentum and the torque. In order to take the relationship between angular momentum and torque, let me take what is the formula for angular momentum. Okay, we have already discussed what is the formula for angular momentum. Okay, let me write here. Angular momentum of the particle is given by, okay, what is the angular momentum of the particle? Angular momentum of the particle, it is given by j vector equal to, that is moment of linear momentum, right? So that is j equal to r cross P, right? Moment of linear momentum gives angular momentum. So this is the definition of angular momentum. Angular momentum of the particle is given by R cross P, right? What I need what now here? Relationship between torque, right? Okay. Now what I will be doing? Let me take differentiating with respect to time t. Let me differentiate this equation with respect to time t, right? Okay, what happens if I differentiate it? dj divided by dt, right? Okay, differentiate this d divided by dt into the bracket, what we say here? R cross p, right? Here, both are changing with respect to time here, right? I need to use UV rule, differentiation UV rule here, right? Okay. If you have two terms here, you know how to differentiate it, right? First, differentiate the first function, that is dr divided by dt cross second function. What is second function? P, right? Plus, keep the first function as it is, differentiate the second one, dp divided by dt. What did I use here? I used UV rule, right? UV rule of differentiation of UV. Differentiation of u cross v plus u differentiation of v, right? Differentiation of the first function cross second function plus first function differentiation of the second function, right? I have used UV rule of differentiation, right? Okay. Now what is this? dr divided by dt, right? So this is the rate of change of distance. Shall I write it as v now here? Yes. So what is v? dx by dt. Here what is that doing? It is nothing but distance, right? So dr by dt, I can write it as v vector cross, what do you get to here? P vector plus r cross. What is it? dp by dt? Yes, it is the rate of change of momentum from Newton's second law. It is nothing but what now here? F. Shall I write like this? R cross F now here, right? Okay. Now let me simplify this. That is equal to v cross. What is this? Linear momentum. What is the formula for linear momentum? Mass into velocity. Shall I write like this? Mass into velocity, right? Okay, what do I get here? Plus, let me take r cross f. Let me keep as it is now here, right? Now, this is a scalar quantity. Let me take it outside. What shall I write? V cross v. Shall I write like this? Okay. What do I get here? Let me keep this as it is. R cross f. Right. Okay. First of all, you need to understand what is the value of v cross v. What is the value of v cross v? Do understand? The value of v cross v is v cross v. This a cross b formula. What is a cross b? Modulus of a, modulus of b, which theta? Since it is cross, we have sin theta here. Right. Okay. This is nothing but v into v sine. What is theta? Theta is angle between a and b. Here theta is angle between v and v. If v and this v both are same vector, then what is the angle between two same vectors? Angle between two same vectors is 0. What is sine 0? Sine 0 is 0. So here, so if you multiply, what do you get here? 0. Right? Do you remember? When a vector is multiplied by the same vector, if you take a cross product of the same vectors, so what is the answer here? 0. Right? Do understand this? So let me substitute here. What is v cross v? It is 0. 0 into something is again 0. What do you get here? That is r cross f. 0 plus r cross f. Okay. What do you get here? Here we will be getting with r cross f. What is r cross f? Okay, let me write like this. That is equal to, we got with r cross f. What is this? Is it moment of force? Yes. What is moment of force? It is nothing but torque, right? So r cross f is nothing but what we say here? Torque. What do you get here? That is dj divided by dt is equal to what we say here? Torque. Right? So this is the relationship between j and tau. This is the relationship between angular momentum and torque. This is how we derived it. So what is the relationship between angular momentum and torque now here, right? That is therefore the rate of change of angular momentum, rate of change of angular momentum is equal to torque acting on it, torque acting what we say here on it, right? The rate of change of angular momentum is equal to torque acting on it, and this is the relationship between angular momentum and torque, right? Is it similar to Newton's second law? Yes. So what does Newton's second law says? F is equal to dp divided by dt, right? In place of F we have torque. In place of linear momentum, we have angular momentum. Thus, we derived it. Earlier, I took directly. Now, I have derived what is the relationship between torque and angular momentum. That is, tau is equal to dj divided by dt. And this is the relationship between angular momentum and torque. Now, let us move on to the next concept. That is, law of conservation of angular momentum. Angular momentum is conserved, but with a condition. What is that condition? Let us check it out. If net external torque acting on a particle is 0. If net external torque acting on a particle is 0, then the angular momentum of the particle is constant. So this is the law, right? What is law of conservation of angular momentum? When is angular momentum conserved? Angular momentum is conserved if net external torque acting on a particle is 0, right? If torque acting on a particle is 0, then angular momentum is constant, right? This law is similar to the law of conservation of linear momentum, right? There also we had one condition. What is that? Total force or a net force acting on a particle is 0, then linear momentum was conserved. In the similar manner, if net torque acting on a particle is 0, then the angular momentum of the particle is constant. If torque equal to 0, angular momentum is constant. And now let us prove that. Okay, for the proof, we have the same steps here. We took angular momentum of the particle and we derived it. We got with the r cross f. Okay, let me continue with this, right? Okay, now what is this r cross f? That is equal to, what is that now here? Tau. So what did we get now here? dj divided by dt, right? Now what is the condition for conservation of angular momentum? Net torque must be 0, right? Okay, if torque acting on the particle is 0, what happens? If net torque acting on a particle is 0, let us check what happens. Okay, in this equation, let me put tau equal to 0. What do you get? dj divided by dt. What do you get now here? 0, right? If differentiation of something is 0, then that something must be what we say now here? Constant. Right? Do remember, differentiation of something must be 0, means that something must be constant, right? Do remember, when torque acting on a particle is 0, then what happens to the angular momentum? Angular momentum remains constant, right? So this is the proof for law of conservation of angular momentum, right? What is the meaning of this? Just understand what actually is the meaning of law of conservation of angular momentum. Come on, tell me, what is the formula for J, right? J is angular momentum. The formula for J is I into omega, that equal to what we say here? Constant, right? J, this is momentum, right? So this is angular momentum. So what is the formula for angular momentum? I into omega, right? I think you remember what is the formula for linear momentum? Linear momentum, P is equal to mass into velocity, right? Similar formula for angular now here, right? For rotational motion, in place of linear momentum, we have angular momentum, right? So I'm speaking about angular momentum itself, right? So in place of m, we have moment of inertia. In place of velocity, we have angular velocity, right? It is similar, right? I omega or mv, that is linear case. This is a rotational case now, right? So angular momentum is equal to I into omega. I omega is equal to constant. If net torque acting on a particle is 0, then this momentum always remains constant here. What is the meaning of this? This is the product. Moment of inertia and angular velocity. Remember, it is not simply a velocity, it is the angular velocity. If moment of inertia increases, what happens to the angular velocity? It must decrease, right? So then only the product will remain constant here, right? If moment of inertia decreases, angular velocity, what happens to here? Increases, right? So the meaning of law of conservation of angular momentum is this: if you increase the moment of inertia, speed decreases. If you decrease the moment of inertia, speed increases, right? So this law is used by the ballet dancers. I think you've seen the dance, right? So it is the dance while rotating here, right? So whenever a dancer is rotating, right, if she open her hands, right, the speed decreases, right? If she closes the hand, the speed increases. What is the meaning of opening the hand? Opening the hand means I am increasing the distance from the axis of rotation, right? Means we are increasing the moment of inertia. How to increase the moment of inertia? We know I equal to mr square. You should increase what we say here, the distance from the axis of rotation, right? So if you increase the distance, what increases? Moment of inertia increases. If moment of inertia increases, what happens to the angular velocity? Decreases. That is the reason if she opens her hand like this, the speed automatically decreases. If she wants to increase the speed, just she closes her hand here, right? When she closes her hand, the distance decreases from the axis of rotation, decreases, I decreases. So what happens now here? Speed increases, angular speed increases now here, right? Okay, that is the reason whenever a ballet dancer wants to stop, right, she ends by extending her hands like this. She will be rotating, and when she wants to end her dance, she opens up her hand so that the speed decreases and she can stop now here, right? So there the law of conservation of angular momentum is used. There are many illustrations for this law now here, right? Whenever the earth, this is a sun now here, whenever the earth rotates about this sun now here, right? So it is revolving like this. When the earth comes near to the sun, its speed increases. When it is away from the sun, speed decreases. Do you understand, right? Whenever the earth is rotating, right, it is revolving around the sun. When it comes near to the sun, its speed, what happens to its speed? Speed increases. Why did speed increase? Because moment of inertia decreases, right? The distance decreases. As it goes away from the sun, what happens now here? This case, moment of inertia increases, speed decreases. That is the reason. If this is the sun, earth is rotating right here, it will be fast, here it will be slow. Here it will be fast and here it will be slow. Again, this is an illustration for law of conservation of angular momentum. Do you understand? If net torque acting on a particle is 0, then angular momentum is constant. So this is law of conservation of angular momentum. Now let us check what is the work done by torque. Okay, to derive this, let me take a rigid body, right? Okay, let me take this is a rigid body which is rotating about this axis, right? Let me take like this. Okay, let me derive the formula for work done by a torque. Okay, let me, what is this? This is a rigid body. Consider a rigid body. Consider rigid body rotating about the axis of rotation. About the axis of rotation. Okay. Now, let me consider a particle here. Let me consider this is center. Let me take it as O. There is a particle at a distance. Let me take that distance is R now here, right? If I want to make this body to rotate, this is the axis of rotation and the body is rotating like this. If I want to make the body to rotate, I need to apply force to it. So let me apply force like this. So what is the force which I am applying now here? F, right? Okay. Let me write about this. Let F be force acting on a particle. Let F be force acting on a particle at a distance r from O now here, right? Let force be acting on a particle at distance r from O. Let me consider this particle, and how much is the force applying now here? F. What is the distance from the fixed point? Let me call it as r now here, right? Okay. Now let F be force acting on a particle at distance r from O, right? And if I am considering this is a force acting on a particle, what happens to this particle? This particle begins to move, right? Okay, it moves through when I apply a force to it, it moves through a certain distance. Let me take that certain distance as ds, right? Earlier it was here, then it came to this position, right? This is the position. Then what is this angle? Let me take this angle made. Let me take it as d theta, right? Okay, let F be force acting on a particle at a distance r from O, and ds with a small displacement, right? Okay, this is a force producing, let me take now here, small displacement, producing small displacement. What is the small displacement now here? ds. Okay, let F be force acting on a particle at a distance r from a fixed point, producing small displacement. What is the small displacement produced now here? ds, right? The question here is, what is the work done by the torque, right? Okay, now to produce this small displacement, let us calculate how much is the work done now here, right? Okay, afterwards let me go with the torque now here. That is the small work done for displacement, small work done for displacement, what we say here? ds. What is the small work done for this displacement ds? We have the formula. So what is the formula for work done? Work done, that is dw is equal to force into displacement. So let me take it as force F, and what is the displacement here? Displacement is ds, right? Okay, now if I am considering this body is rotating in a circular manner, we have the formula for S equal to r theta, right? We have the formula for radius into angle, the length of the arc, right? This is the length of the arc, radius and angle. There is a formula. So what is the formula? S equal to r theta. So this is the arc now here. What is the arc now here? ds. Shall I write like this? Arc is ds. What is the distance? Yes, of course it is r now here. What is the angle made now here? Now the angle made is what we say now here? D theta now here, right? So this is the formula, right? I applied this formula here. What is the length of the arc? ds. What is this radius? r. What is the angle produced? d theta. Okay, shall I substitute here? Okay, what do I get now here? That is equal to F. In place of ds, shall I write r into what we say now here? d theta, right? And we have the product of force and distance. We know the product of force and distance is nothing but what now here? Torque, right? Torque is a moment of force, right? Shall I write torque tau into what we say now here? D theta. So this is the small work done, right? I need to convert the small work done into total work done, right? So this is for small displacement d theta, but the body rotates like this now here, right? It rotates with the larger angles. To convert small to larger, let me go with the integration now here, right? Okay, now let me calculate what happens to the total work done by the torque now here, right? Okay, let me take now here, what is the total work done? Okay, shall I take like this? Total work done means integration of dw, right? Integration of dw. Shall I integrate this side also? What do you get? Integration now tau into what we say here? D theta, right? Okay, so tau means the torque which I applied by the constant torque. Let me take the work done by a constant torque now here, right? So let me remove it outside. What do you get? Integration of d theta, right? So if I am taking integration of d theta, it is theta itself. What is integration of dw? That is w. So this is the work done. What is the work done by a torque? Work done by the torque is given by tau into what we say here? Theta, right? Is it similar to the linear motion? Yes. What is the formula for linear motion? You know. What is the formula for work done by a constant force? Right? So work done is a force into displacement. Is it similar? Yes, it is similar. In place of work, we have work. Okay, that is the same thing. Work done by a torque we are speaking now here. So instead of force, there is torque, tau. Instead of distance, here there is angular distance, right? So if it is traveling, we call it as a displacement F now here. Since it is rotating, we call it as angular displacement. This is the linear displacement and this is the angular displacement. Even the formula for work done by a torque is similar to the formula what we have for the linear motion. So work done by the torque is given by W is equal to tau into theta, right? Work done is the product of torque and what we say here, this is angular displacement, right? So W is equal to tau into theta is the work done by the torque. So this was all about torque. Thank you.